All right. Example 10. Differentiate. That's a real popular term in educational lingo, right? Right? It's one size fits all curriculum, but then you need to differentiate, which is kind of what we do in here, right? We're all learning the same thing, and now we're about to differentiate. It says y equals arc sine of x plus x squared root of 1 minus x squared. Differentiate and then simplify to a single term. All right, so before we differentiate, we take inventory. We have two terms, so it's like two little problems in one. Three if you consider the left side, which I will. Do any of those terms need to be rewritten so that we can differentiate them? Yeah, the second one. Now, you're probably at the point where you don't have to rewrite it because you can just think of that quantity to the 1/2 power. And that's fine if you're at that point. I respect that. It's kind of where I want you to be. But for illustration purposes, and maybe to just avoid a careless mistake, because it's one of those days, I'll go ahead and take the time to rewrite it. All right, so here we go. The derivative of the left is dy dx, or y prime. Arc sine of x, the derivative arc sine of x. Y'all memorized them over the weekend, did you not? Good, 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 good. We'll quiz tomorrow, and I'll probably just have you list all 6 of those, and then a couple of questions like this where you're using them. Now, what is the rule that we use out of the box on the second term? Product rule. So if you want to, again, even add grouping symbols there to help you see factors, that's fine. 2 factors means 2 terms. The derivative of x is 1 times the second one goes along for the ride, plus x times the derivative of the second is now the chain rule. Blob to the 1/2 becomes 1/2 blob to the what power? Negative 1/2. Most of y'all know 1/2 minus 1 is negative 1/2. But what's easy to do is to forget to even write that exponent, because you're writing down the information in here inside first, and your mind kind of shifts tasks to take inventory. So be careful. And then times the chain rule, the derivative of 1 minus x squared, which is negative 2x. And then I'll close it for that whole derivative right there. All right, so now it says to clean things up. So we'll go ahead and do that. Clean things up. Then simplify to a single term. Now, if you notice, yeah, we're going to be able to factor some things out. I got some 1 minus x squareds over here. One of them is a positive 1/2, one's a negative 1/2. This one over here is in radical form. I think I'm going to put it in rational form so that they're all written as powers. It'll be easier to combine that way. So we got dy dx equals, that'll be 1 minus x squared to the negative 1/2 plus 1 minus x squared to the positive 1/2. And then this last term needs some serious help. The 1/2 and the 2's divide out, and we're left with a minus x squared times 1 minus x squared to the negative 1/2. All right, now it says to combine into a single term. I have 3 terms. Are they like terms? They're not like terms. But I can factor out least powers, which is what we're going to do. We'll get accustomed to this by doing it many, many times. We're going to factor out the smallest power up there on the 1 minus x squared, which is the negative 1/2. All right, that includes smallest, including negatives, not just magnitude. And I always go at this point with the brown bracket. In this case, I'm using brown, so it's the beefiest of all brackets, the beefy brown bracket. And, of course, the first term, when you factor it out of itself, you're left with 1, not 0, but 1, not 0. On the second term, remember when you factor out, you're dividing out, so it's really what we started with divided by what we're factoring out. And so you subtract the exponents. 1/2 minus a negative 1/2 makes it 1. So we're just left with a 1 minus x squared. Now, I'm not even going to put it in parentheses like that. You could, or even to the first power to show kind of the associations. But because there's nothing to expand and nothing to distribute but a positive 1, having the parentheses gone enables you to then collect like terms later. And on the last term, we're just left with x squared. Now we're ready to put it back into radical form. So since the first factor is negative, it's going to go to the bottom, so we'll have a denominator. The fact that it's 1/2 puts it back under the radical. So we have 1 minus x squared. And notice in the numerator, we have 1 plus 1. So that's a 2. You impressed? And then minus x squared is minus 2x squared. And so right there, we've met the requirements. That is a single term. It's a single quotient. But if we stop right there, we're missing a nice opportunity to simplify it even more. What can we still do in the top? Factor out a 2. Yeah. So if you factor out a 2, you're left with, holy moly smokers, 1 minus x squared. Which now in the denominator, maybe I'll put that back as 1 minus x squared to the 1/2 instead of the square root. And add a little 1 up there in the top, because now I'm dividing and my bases are the same. So what can I do with my exponents? Subtract them. 1 minus 1/2 is 1/2, which means now my final answer I can put back under a square root, 1 minus x squared. And that, I think, is about as far as we can go, unless, since 1's a perfect square and x squared's a perfect square, we can call that 1 minus x. That would be going too far. That is not correct, so don't do that. Yeah. Those are terms. You can't take the square root of individual terms. But there you go. That whole derivative simplified to something pretty darn nice. So then later on, if we were going to be using the derivative for something, this would be much easier to use moving forward. So notice that the calculus was on this line. Here's the calculus line right there. And then all the rest of it was just algebraic manipulation. It's the biggest obstacle to mastering calculus. Or you get the most practice with your algebra skills doing calculus. And I think there's one on the worksheet that's similar to that. I worked it this morning because I'm in the process of working that key. So the one that's in here, it doesn't match up 100%. Okay. Wow, I got through a problem error-free. That's the first one for the day. Hope it's not the last one. It was the pumpkin chocolate chip cake. We'll say that. All right. Number 11. Find the coordinate. Co means what? Yeah, coordinate means point, right? But co means share, and an ordinate is like an x or a y. So coordinate would be x comma y, typically. Of any tangent, that means tangent line. It doesn't have to say line, but that's any tangent line. And find the equation of any horizontal asymptote. All right, so tangent line and horizontal asymptote to this graph. Well, let's do the horizontal asymptote question first, because that's kind of a review question. How do we show the analysis for horizontal asymptote? Oh, not G prime. Horizontal asymptotes, remember, are what type of asymptote? End behavior asymptote. So that's the limit as x goes to infinity, and the limit as x goes to negative infinity. Review question. So remember, with the limit, you could actually take the limit inside and then square the result. So what's the limit as x goes to infinity of arctangent of x? I guess I forgot the x there. Pi halves. And then you square the result, so you get pi squared fourths. And on this one, the limit as x goes to negative infinity of arctangent is, negative pi halves quantity squared, which turns into pi squared fourths again. And so this graph would have a single horizontal asymptote at y equals pi squared fourths. The graph would look something like this. It takes all the y values from arctangent, and if it squares them and makes them a little bit bigger if they're bigger than 1, and then makes them a little bit smaller if they're less than 1. So it's going to look something like this. It'll have y-axis symmetry, and it'll be right there at pi squared fourths. All right, pretty neato. So that takes care of that. But now, since if that's what the graph looks like, since it's an even function now, can we answer the horizontal tangent question without doing any calculus? There should be a horizontal tangent where? At the origin. Right, let's verify that. We will need the derivative, so let's find g prime. That's what we need for the tangent line. So g prime of x by the chain rule, that's 2 arctangent of x to the first times the derivative of arctangent of x, which is 1 plus x squared to the negative first, or 1 over. See how I caught that careless mistake? To the negative first, or 1 over. 1 plus x squared. All right, so I'll just go ahead and rewrite that because I'm about to use it. I'll put the 2 arctangent of x in the numerator. So now it's a single term. That looks pretty nice. And you always want to show the equation you're solving. So whether you're plugging in for x or you're setting it equal to a number, show that. In this case, we're setting it equal to 0 because we want horizontal tangents. And now, when is a fraction equal to 0? Right, 0 over non-zero, so we'll just set the numerator equal to 0. In fact, I like 0 over non-zero better. I'm going to set it equal to 0 over non-zero. I like that. And if you divide through by 2, you get arctangent of x equals 0. And now to solve, what is the inverse operation of arctangenting? Tangenting. So if you take the tangent of both sides, tangent of arctangent of x is x, and you're left with tangent of 0. And what is tangent of 0? 0. Yeah. Now remember, 0 over 0 you would throw out. It could be that the graph of arctangent looks something like this. If it had a cusp there, that would not be a horizontal tangent, would it? It would be undefined. So does a x equals 0 cause a 0 in the denominator as well? No, it causes a 1, all right? So 0 over 0 you throw out. Is this graph of arctangent going to have any vertical tangent lines? That is the denominator ever 0? Is 1 plus x squared ever 0? No, that's a parabola. It has a y-intercept of 0, 1. It's 1 at the very least. So that's why the graph looks kind of like the purple graph there. There's no vertical tangents. So x equals 0. So now the coordinate, I put 3 zeros there. I'll just leave it. The coordinate, or the point, is 0, comma, and now I plug it back in over here. What's arctangent of 0? Tangent of what angle is 0? 0. 0 squared is 0. So it was the origin. I'm going to take one of those O's out of coordinate after all. There we go. So it was the origin. So sometimes you might be able to answer like on multiple choice questions, or just to satisfy your own curiosity, you can answer calculus questions kind of based upon what the graph looks like without actually having to do a lick of calculus. But maybe you didn't know what the graph looked like, and that's fine. That's why we have the calculus. All right, any comments or questions about this dude? So good so far? So far, so good? 6.02 times 10 to the 23rd. That's like 6 heptillion. That's a very large number. Supposedly, if you take all the sand on the Gulf Coast, 3 feet deep, like you had an excavator and you went all around the Gulf Coast, all the way to Florida, all the way to South Texas, 3 feet deep, all the sand, you put it in a pile, and then you went through and counted 1, 2, the grains of sand, 3. That would be about 6 to the 23rd. 6 times 10 to the 23rd. 6 heptillion. 6.02214. I think they have counted 8 decimal places after the 6. Okay, which is enough to define supposedly the kilogram for most people's satisfaction. So anyway, a pretty interesting number, Avogadro's number. Avocado's number is, I think you need probably at least 2 for a party of 2. All right. With the thought being that one person can eat a whole avocado themselves. All right. Example 12. Rewrite tangent of arc cosine of x squared as an algebraic expression. Not even a calculus question at all. We've kind of already done this when we did the derivative of arc sine. All right? If we think back to the days of pre-cal, when we were much younger mathematically, this x squared represented a what? An angle or a ratio? It did represent a ratio. So we've already done it in this section. We'll put it over 1. If I take the arc cosine of that ratio, I'm going to get an angle theta. I don't want theta, though. I want the tangent ratio of that angle theta. So what we'll do is we'll come over here into quadrant 1. We'll drop a perp on some generic terminal ray defined by the independent angle theta. And now I will list the two sides based upon the x squared over 1 ratio. Cosine is in the SOHCAHTOA, it's the CA ratio, right? So it's adjacent over hypotenuse. Or you can just say it's, in terms of x, y, and r, it's x over r. So in this case, x is x squared, different x's, and r is 1. And then by the P theorem, which is a theorem that says if you drink a whole gallon of water, you're going to have to use the bathroom sooner or later. Or the Pythagorean theorem is what I meant to say. What is the third side? Yeah, the square root of 1 minus x squared. Very good. It's the square root of hypotenuse squared, 1 squared, minus x squared squared, which is x squared. Not even. It's x to the what? 4th. Right. X squared is x to the 4th. So be careful. Make sure you always check your work. All right. So now we have all three sides in terms of x. I want the tangent ratio. So tangent is OA, or y over x. So it's going to be this guy here, 1 minus x to the 4th, over the horizontal, which is x squared. All right, so that's kind of nifty, because really we have a trigonometric representation of something and a algebraic representation of something, and they're identities. They're replaceable. They're mathematical synonyms. So if you ever are given something like this, and it's a multiple choice question, and all your answers are in terms of x, you can convert it first and then take the derivative. Or if you have something like this on the right, and all your answer choices are in terms of trig, you can deconstruct it and make it look like this. That's probably not going to happen, because that's a lot harder to deconstruct. In fact, you can actually deconstruct it into several different things. But tangent of arc cosine of x squared can only be algebraically expressed one way. All right, so why would I throw that as a review question in here? Yeah, we might quiz over it. Very good. And it's a good segue into example 13 also. Example 13, here we are. A multiple choice example? Woo! Find the derivative of cosine of inverse tangent of x over the square root of 6. A, B, C, D, E. C, we're done. Love those multiple choice questions, especially when they're just graded on completion. All right, so let's actually do it. You have two options. You could take the derivative right here using the chain rule. There's 3 layers, right? The outside layer is cosine, the next inverse layer is arc or inverse tangent, and the next over the square root of 6. But if you do that, it's going to be like negative sine of something, of inverse tangent, blah, blah, blah. What do you notice about all your answer choices? The denominators are all the same. They're all equal to f prime. They're all on page 8. How keen you are. None of them have trig in them. None of them have trig in them. So, with the idea that an ounce of prevention is worth a pound of cure, or simply simplify early and often, we should probably convert this to an algebraic equivalent expression prior to differentiating. Otherwise, we might have more work to do on the back end. All right, so let's go ahead and do that. We're going to do that the same way we just did on the previous problem. Inverse tangent is going to give us some angle theta. So we'll label the sides now. Remember, that's the tangent ratio, so that's y over x. So yes, we're calling y x here and x squared is 6, correct? It's the opposite over adjacent ratio if you want to do that. And now the hypotenuse by the Pythagorean theorem is the sum of the squares of the two sides. So that's x squared plus the square root of 6 squared is 6. Yeah. There's no difference now in your radicand because you're finding the hypotenuse, not one of the short sides. All right, so now we have all three sides. We can just pull off the cosine ratio. Cosine is adjacent over hypotenuse or x over r. So that's the square root of 6 over the square root of x squared plus 6. Wow, that's pretty nifty. In fact, that looks almost a whole lot like some of the answer choices. A lot closer to it. All right, so now we'll take the derivative of that. Do you want to use the Hody-High rule? Me neither. So let's go ahead and rewrite it and use the what rule? The chain rule. Yeah, not the Shane rule. That's different. That's the don't come back after you say you're leaving rule. That's the Shane rule. I'll explain that later. The chain rule is what we're using. So we bring the whole quantity to the top to the negative 1/2. Now we'll take the derivative, f prime of x. The square root of 6 is a constant multiple, goes along for the ride, or if you want to absorb it into the derivative using the chain rule, times negative 1/2, you get negative square root of 6 over 2. There's your new coefficient. Times x squared plus 6 to the what power? Negative 3/2. Good. Times the derivative of the inside function, which is 2x. And now all we have to do is simplify. The 2 from the chain rule and the 2 or the 1/2 from the chain rule divide each other out. And if we simplify it now, in the numerator we're left with a negative square root of 6x. And the x is outside the radical, yes? So make sure the radical only covers the 6 and doesn't extend over any part of the x. Very careful. And then back in the denominator, notice your answer choices are not in radical form. They're still in rational form, so we'll bring that quantity to the bottom, and we'll just say it's to the positive 3/2. And now it's just a matter of identifying what the right answer is. Of course, what did they do with their negative? They moved it out front and put it on the same level as the division bar. So look for that, and then you got answer choice E showing up as the right answer, which it's a good thing we worked it out because we were going to answer C otherwise, and that's wrong. But E is correct. All right, now before we kind of walk away from the problem, let's say you don't size it up. Let's say you don't even make that connection on your own like, hey, I should probably convert it first. You're like, you know what? I know how to take the derivative of this. I've been practicing my trig and inverse trig derivatives, and I want to show those off. So here we go. F prime of x. The derivative of cosine of blob is negative sine of the blob. Inverse tangent of x over the square root of 6. Okay. Times the derivative of the blob, which is inverse tangent. That's 1 over 1 plus blob squared. Times the derivative of the blobbiest of all blobs, the derivative of x over the square root of 6, 1 over the square root of 6. All right. Wow, that's the derivative. That's correct. Now we just have to match that up to one of these dudes. And it looks to me like it's E. Yep, it's E. I can tell. I can tell because there's a negative there and there's a square root of 6 there, and that's E. Yeah. You know what? You're a long way off from calling E the right answer. Guess what you're going to have to do anyway with this thing? The thing we did with this. And then you're going to have to bring it into the fold and then incorporate all of this garbage into it, right? So, yeah, if you want to finish that on your own, good luck. Have fun. All right, so that's using the chain rule after we converted it, right? Not before we converted it. What's the chain rule? The chain rule is don't come back once you say you're going to be leaving. Okay? And the reason is, Alan Ladd is the reason. Alan Ladd is the reason. In the classic movie, yeah, y'all aren't going to be able to hear this because it's still playing through my earpiece, but in the classic Western movie Shane, starring Alan Ladd, at the end of the movie, or maybe you've read the book. It's like one of those 8th grade books that some students read instead of Red Badge of Courage. Did y'all read Red Badge of Courage instead? Johnny Tremaine? Anyway, at the end of the movie, Shane, who is a drifter, a high plains drifter, not unlike Clint Eastwood, comes and helps a widow and her son, and at the end of the movie, he leaves the family, and the little kid is torn up about it. And you can't hear, so I'll say what's happening here. Okay, so here's the last 11 seconds of the movie. The very end of the movie. Shane! Come back! And that's it. That's it. There wasn't like a Shane 2, the sequel. Shane comes back. He never does. The kid is crying, and Shane, the movie ends, and Shane is gone forever. So, and Shane said he was going to leave. He said he wasn't going to stay and become a permanent part of their lives. So the kid shouldn't have got too attached. It was kind of his own fault. But he didn't have a dad. So anyway, we're done with this.